two events are independent of one another, if the outcome of one event doesn't impact the chances of the outcome of the other event. Okay, in other words, and by the way, I don't know whether it's yes or no yet. I haven't finished the problem, but in other words, the probability of A, so like event A, maybe the probability that it rains, given that it rained yesterday, if that is equal to the probability of A, then the two events are independent. So just to translate this from math into English, this says the probability that event A happens, given that event B has already happened, is equal to the probability of event A happening without even thinking about event B. So an example of two things that are definitely independent. You flip a coin, you get a heads. Then you roll the dice. The heads didn't impact your chances of getting a 6 or getting a 5 or getting a 4, right? The heads has nothing to do with rolling the dice. So who cares what the event B is? The probability of A is still the same. And that's basically what we're doing here. They're asking us to calculate the probability of having a $450,000 to $600,000 home out of all these homes in their selection, given that a 3-bedroom home has been selected. So the probability that we select a $450,000 to $600,000 home, given that 3 or more bedrooms are present in the home, that's a conditional probability. That's saying, hey, it's no longer a question of yes or no to this to the 3 or more bedrooms. We're saying yes, you're only thinking about 3-bedroom homes. So when you calculate a probability, you take the number you're interested in. In this case, it's the number of $450,000 to $600,000 homes. There's 136 that fit in that category that are also 3-bedroom homes, right? Because again, it's a conditional probability. When they say this vertical bar, it means given that it's 3 or more bedrooms. That means we don't even look at this column. We don't even look at the no column. We're just looking at the yes column for this problem. So the 136 is the number I'm interested in, and I'm going to divide that by the total. But again, it's only the total for the yes column because it's a conditional probability. We're only thinking about the homes where they said, yes, we have 3 or more bedrooms. So the total for this is 665. Okay, so we divide those. That's 0.2045. So they want the third decimal place, so we're going to say 0.205. Okay, that's the first probability. And then the second probability, the probability that you have a home that's $450,000 to $600,000 home, there's no condition there. So let's first calculate how many homes there are that meet that quality. There's 136 plus 302. So there's 438 homes that are in that upper price range out of a total of 1,739 homes. Oh, I said that wrong. 1,793 homes. So that probability is 0.244. Okay, so in practice, I would say yes, those appear to be independent because they're only off by like a little less than 400ths, right? That's pretty close. But because this is my math lab, they're not exactly equal to each other. We would say yes, they are independent if the probability of A and B, the probability of being the more expensive home and having home prices and having 3 or more bedrooms, if that was equal to just the probability of home prices without the condition, right? If this held. Since they're not equal, though, we're going to choose no for this question.